This, and the other learning resources in this course have been made possible by funding from the European Commission's Erasmus Plus program.
Bon, I would like to talk a little bit about data management. So actually you have seen a lot about laser scanning in general. Actually, some of the material has been covered twice already. So I think you really have a solid background on it. I will present this presentation to a certain extent because at a certain point we will discuss in this presentation about point cloud registration, and for point cloud registration I made a dedicated presentation for that. So as soon as we reach that point we will go to the other PDF, but normally I have just opened these presentations. So the presentation of today with some videos, as well as section 5, so point cloud registration. You can also find the presentation there. It is open. And after the remarks made by some of you that some of the things were not visualized yet, I made sure that everything is visualized in this case. So let's speak about data management. And of course, once again, if there are any questions or if there's something not very clear, you can just interrupt me. So the big thing about laser scanning, you are aware of the fact that if you use a laser scanning, you're able to acquire a lot of points. And this is a very big advantage, but also a very big disadvantage. So for example, if you have a site somewhere and you have the option to use a total station or a laser scanner, it is not per definition a good idea, always a good idea to use a laser scanner. Because with a total station, if you have a very simple object, for example, a room or just a rectangular area that you want to measure, you set up your total station, you measure 1, 2, 3, 4 points, and you're ready to go. After, of course, setting your backside or using your resection. Whereas if you would use a laser scanner, the data acquisition itself goes very fast, very smooth, and highly automatic. So that's where we are in this case. So high automated data acquisition. But as soon as we have to go back to the office and we have to do our data processing, for example, in this case, in this example, just the extraction of 4 coordinates of the corner of an object, it is not very convenient to use a point cloud for that. And because of the fact that most, I don't say everything, but most of the modeling procedures, so the extraction of information out of your point cloud data still has a very low level of automation. And registration, that's what we will discuss after this part of the presentation, is something that is somewhere in the middle, fortunately. So I made a very short scheme to give you an idea of the different steps that have to be considered during an entire campaign where you would use a laser scanner. So first of all, and this is actually exactly the same as what you will have with photogrammetry, you will have to set your project requirements. What is the resolution? What is the point density? What is the accuracy? What should be measured? What are the environmental conditions? All these questions should be answered before you even use the appropriate data acquisition technique. Like you would do, of course, with photogrammetry. If you would apply photogrammetry on an archaeological site or a museum, you will not just go to the museum and start making pictures. No, you will first look at the object, where to take my photos, what is the required ground sampling distance. So there's a very interesting parallel in defining the project requirements. You will do your survey planning. So even with a laser scanner, and notwithstanding the fact that we do a lot of highly automated data acquisition, we still have to plan our data acquisition because of the cast shadow, or the shadows that we will generate, because of the fact that we have to position our laser scanner in 1, 2 or more places. We have to set our targets and stuff like that. So that requires also a certain amount of effort. And then, and only then, if all the requirements are set and all the survey planning has been accomplished, we can do our field operation. So we can start doing our actual data acquisition. Then back in the field, or as soon as we pick up our laser scanner, we finished with the field operations, we do data preparation, data registration, and further data processing. And all these parts of the process should meet certain specifications. So at the end, after doing setting your requirements, planning, operation, preparation, registration, and processing, you will do, of course, data archiving in order to make sure that your data is stored somewhere in a sustainable fashion. You will do your data delivery. So you make your deliverables and you see if your data meets the specifications that were set at the project according to the project requirements and according to all the other different steps. And we will cover different of these parts in the coming presentation. So first of all, we have to plan our survey, plan our data acquisition. The requirements and the instruments that you will have are of course heavily depending on the projects, the properties of the project itself. So if you will have to make a 3D model of a piece of pottery, or you will have to make a 3D model of a site, or you will have to make a 3D model of an entire city, these different types of projects will require different types of data acquisition and sensors that are to be used. For example, are we able to just measure some simple lines, some simple points? In that case, we can use a GNSS, a Global Navigation Satellite System, or GPS if we only limit ourselves to an American system. Or if we do it in a kinematic way, we can work with positioning and orientation systems, use LiDAR data, and work with sequential strip registration, make our DEMs, digital surface models and digital terrain models, and work in that way. So that's for large scale areas. Or we can work on animations by just filtering and register our point clouds, make some flight throughs to it, and as a result, we will have some MP4 or MKV files that we can use as some kind of a flight through animation. Cross sections will have a different way, and even just animations in terms of 3D modeling with textured maps, 3D models, that requires a different procedure. So always start with the question, okay, what is required from the project, and what are the people asking about 3D or about spatial data in general? And that will define the sensor that you will be using and the different processing steps and data acquisition steps that will follow. So project description is extremely important, and that's why in the exercise that I present you in the introduction of laser scanning and in the introduction of photogrammetry, and it will also come back in a general task that we will discuss in one of the coming days, it is required to thoroughly discuss the project itself. So what will be modeled? What is the study object? What are the quality requirements? As a land surveyor, especially at the beginning when I start working with my colleagues from the arts department, they said, okay, we have a piece of pottery and we want to have it measured in the map of the archaeological site with sub-millimeter accuracy. Where was it found? Yeah, somewhere over there. So there you have a discrepancy between precision and accuracy, and you have to find an equilibrium between quality, precision, correctness. And even if it is not possible to fine-tune these quality requirements, I believe that it's the task of the master of the 3D technique, so the master of the data acquisition and the processing, and the person who is involved in the deliverables, at least to steer the discussion on saying, okay, if you're not able to define your ground sampling distance or your point density, what do you think about these densities or these quality measures or something like that, so that at least you're able to steer that discussion. And then of course the context, what is the finality of the project, what will be done, who will use the data, what is deliverables are required. And then after all these questions, you can ask yourself, okay, is laser scanning suitable for this project, or should I use other techniques like photogrammetry or just conventional topography or airborne data acquisition? Then as soon as this is set, you can go on site, do your terrain study, look for challenges, look for obstacles. Is it safe to measure? Are people passing by? Do I have to take security measures in terms of putting pylons around my site, or mark the sites possibly. And then, assuming that we start with a laser scanner, you can define the optical scan locations and determine the optimal target locations. And then after data acquisition, you also have to work on your data management. But actually, this is also a good idea to think about this think about this topic on data management on forehand, to know, okay, I have my laser scanner, where will I store all my data? Do I have a data management system? What about data filing or file naming, that you have that straight on forehand? The scanning locations, you will have something like this. So actually these screenshots, they are a little bit dark, but what you see here is a scanner with around it the different targets. And as you can see, the person that made this drawing, he only put his targets on the same level of the laser scanner itself. So the variation in X or in Z is very limited. It is of course much better to have an equal spread of your targets around your scanner. So not only in X and Y, but only in Z. And even then, not only on the object itself, but also try to make some kind of a network where the targets are around the object itself, so that you have a nice 360 coverage of your targets. And that's why you also see a target here behind the scanner. The scanning locations are very important, and that has also been discussed by Michele yesterday, because we are not sending a pulse with an infinite thin dimension. This spot actually has a certain size, so it has a dimension, and this dimension will increase as a function of, first of all, of the distance between the scanner and the object. So the further we are away from the scanner, the larger our spot size will be, but also the incidence angle. So the angle at which my laser spot is being reflected by the object itself. So if we have a scanner here, we have an object here, we will have a very large incidence angle in this case, and we have a very low incidence angle in this case. And this obviously has an impact on the size of our spot width. So this is the ideal situation, just a perpendicular radiation of our object, where we actually just have a circle. And the larger this incidence angle, the larger our spot will be. And you will see in a few slides that this also has an impact on the geometric quality of the object that we are scanning. So you will have to take this into account. Then on target locations, I already mentioned that we have different types of targets, like with the C10 scanner that I used for the measurements in my village. I use these kinds of targets. And then based on the difference in reflection, the scanner automatically detects the center of the target itself. But there are also targets that you can use also for photogrammetric data acquisition. So these black and white targets, and then there's software that automatically extracts the center of this target, the black and white squares. And spherical targets, it's also very interesting, because what's actually happening here, you make a scan of the sphere. So these are just spheres that are put on a tripod. And if you make a scan of it, you will have a spherical part of a spherical surface. And then you can ask your software to detect spheres in your data point cloud. And then the software detects actually the virtual center of all these different spheres. So these are then the coordinates of your ground control points of your targets. They all have advantages and disadvantages. Like in general, I would say that this is the most accurate way of defining your coordinates, because it's based on geometrical measurements. And another big advantage is that if you have a scanner from one position and you have a scan from another position, that in this case, you don't have to rotate your target. You're just measuring the surface of the sphere, and the point is extracted or calculated in a systematic way, in a coherent way. But in this case, you will have to rotate your target in the direction of your scanner because of this phenomenon. the increasing size of your spot size. But on the other hand, one of the advantages, for example, of these types of targets is that it's very easy to print them. So you can just print them for free, like I just discussed with Jane, I think. You could just go to your printer, print some black and white targets, and it's very easy to put them just with some tape or put them somewhere with a stone. So in any case, some general guidelines that I would like to give you. Of course, more is better on the one hand, because the more you cover, the more points you will have. But of course, more is not necessarily better, but because more points also include some kind of an over measurement and over dimensioning of your object. So try to cover as much as possible per scan. So try, if you position your scan, make sure that you see as much of the object of study as possible. But if you overscan it, if you increase the numbers of scans, it also increases the amount of data, the amount of space that you will require to save all your data. It will be more demanding to process these data. So you have to find a balance between what is necessary to measure. Of course, try to limit that, but cover as much of the object as possible. Regarding the target placements, of course, you have to make sure that that you will have to place at least, and definitely at least, 3 targets per per scanning location, and all these 3 targets should be visible, preferably from at least 2 scans. So per scan, a minimum of 2 targets, and every target should be measured at least twice. Let me go to my webcam to make sure, because I have my notebook with me. I will go to the. Yeah, voila. I'm not quite sure if it's not visible. I will make a scan of it. But this was my my workbook. So what you see here, I hope you can see it. This was the object of interest. So I had access to the front side of that object. You will see the different scans. These are the little triangles that you see. One here. I think there is one here, and I have one here and one here. And also what you see here is that the targets are situated nicely around my scans. I made a line of the visibility, so visibility lines indicating what scanner saw what target. And there was also a target that was only visible in one scan. That's a target I obviously had to eliminate from my data acquisition. So target placement, at least 3, because with 3 targets, you can define your coordinate system. So you have a redundancy of your X, Y, and Z axis. Target measurements. There are 2 options to do that here. In this case, if you want to use targets, you can either measure your targets yourself. And by the way, that's another advantage of these types of targets, that you can use your total station to resect, for example, in your absolute coordinate system. So if you're working in the Greek national grid, you use some GPS measurements, you resect yourself based on these GPS measurements, and from that total station, you can measure all the centers of these coordinates in the Greek national grid with the correct elevation values, or in UTM, or in any other coordinate system you would like to use. In the other cases, you will have to do a forced positioning. That's something we will not discuss, but with the total station, it's very easy, of course, to measure these coordinates of the black and white targets. So you can do that with a total station. If it is suffice to work in a local coordinate reference system, so just a arbitrary coordinate reference system where the only constraint is your Z coordinate or your Z axis pointing upwards, in that case, you can just take the first scan, calculate the targets for that, and then sequentially link all the targets of all the scans based on the first coordinate system. And that's also something we will do in the demonstration while talking about registration. And targetless scanning, so scanning an object without using any targets, is just a cloud-based registration that will take place. We will also discuss that in more detail in the next presentation. 2 very important guidelines as well is that you have to consider safety environmental conditions. Be sure that if you use your total station, that it is safe to use it that you're of course allowed to use it, but I think that goes without saying. But that's also safe for both the operator as well as the scanner itself. Look for a stable ground, don't look very steep slopes and stuff like that. And always consider crowds, so people walking around on the site. In general, I must say that people are very interested in topography, and in laser scanner they see something rotating with a lot of lights and making a lot of noise. So people are interested in it. They will look on your device, on your laser scanner, and the last thing you want to do is at first harm these people because they are looking into the laser beam, and secondly that they destroy your measurement, or even worse, destroy your scanner by touching it or dealing with it in an inappropriate way. So in that case, it's always good, if you know that there are people walking around, to have an observer next to your scanner, and maybe to explain a little bit what you're doing. So also for community engagement, it's very good, but also for the safety of the people and the scanner itself. Then field preparation and data preparation. So assuming that we know about the conditions of our site, we can start our preparation, walk on the site, see what has to be scanned, getting some kind of a feeling of the site, know where we can position our scanner, some virtual preparation that we're doing here. And then we can position our scanner, our targets, start the scanning, optionally connect it with our laptop, configure our scanners, check the parameters, and do the scan itself. So the scanner itself, we already know the properties of the scanner. So we discussed about that yesterday and on Thursday. A vertical axis always pointing upward, so you have to make sure with the bubble, I'm not sure, just for the people that are not familiar with it, topography bubble Treibach, I think it's called the Treibach. So you have something like this. That will allow you to set the vertical axis pointing upwards and perfectly upwards. And also with the registration, this is a very useful property to incorporate in the registration itself. So make sure that you have a stable background, that at least that during the data acquisition that your scanner is working, that it's not vibrating too much, or that it's not going away with the slope or something like that. So use a tripod, try to use a tripod. Make sure that it's properly leveled, excuse me. And it is also accessible during the full scan. So if you're putting your scanner somewhere and during the scanner there's a van blocking your object, or a fence is being closed or something like that, try to avoid that. Make sure that you always have direct access to your scanner. Regarding the stable surface, especially in urban environments, this can be quite tricky. Like for example, one thing that I would advise you to avoid is that you position your scanner on highly vibrating surfaces like bridges or metal plates near rail constructions or highways or something like that. So always try to make sure that you have a solid, stable surface underneath you. Most scanners have a field of view, an horizontal field of view of 360 degrees. So it is very good to also use this full 360 degrees. So if you have, for example, a room that you want to cover with one scan, make sure that you put it nicely in the center, for example, and then you will have a nice 360 coverage of your scanner. And most of the scanners, they will have a certain, or all the scanners will have a certain vertical field of view. And depending on the specifications of your scanner, it will vary a little bit based on the depth view, the no data view of the scanner itself, because of the fact that the scanner cannot scan here because there's a tripod and a scanner blocking the view. And based on the configuration of the scanner, you will have a value that can vary from, in this case, 25 degrees, but also 30 degrees, 50 degrees, or 2 times 20 degrees. So you will have to consider that, because it will obviously result in gaps in your data. And then, as soon as you have set your scanner, you will have to decide on the scanning resolution. Now, primarily, this scanning resolution is depending on the project specification. So the project owner will say, okay, I would like to have a point cloud with a point spacing of 1 centimeter. So on every part of the object, I want it covered by 1 point per centimeter, or 2 points per centimeter, resolution of 5 millimeters. And as already told also by myself as well as by Michele, this is not a simple parameter that you can set in your scanner, because of the fact that it has a certain angular increment, and this angular increment also involves that you will have a varying point density based on the distance away from your scanner. So you will have to decide on your point density based on the distance from the scanner to the object itself. I have a screenshot here of a Leica P40. And this screenshot will actually shows you that, okay, if you have, for example, a distance of 10 meters with a given resolution here. So what you set here is you set the distance from the scanner to the object, and then based on that you can play with the resolution, and it will say, okay, in this case I have 6.3 millimeters resolution at a distance of 10 meters. And you can play with these values as a function of the distance from the scanner. But of course, an increased resolution will also increase your data acquisition time. So just for your information, I'm giving here a table also for the Leica P4, indicating the duration of a scan. When you say, for example, I want a resolution of 5 centimeters per 10 meter, 2.5 centimeters, 1.25 millimeters, up to an eighth of a millimeter at a distance of 10 meters at normal sensitivity or high sensitivity. So that will depend on the power that is emitted and the reflectance that is accepted by the scanner itself. The impact of that is demonstrated here on the right image, where you see a high density or illustration of a high density scan in comparison with a low density scan. So the scan spacing, the point spacing, will differ as a function of the resolution that you're using here. And important to memorize here, or to keep in mind, is that the resolution is expressed as a distance, so a point spacing as a function of a certain distance from the scanner to the object itself. And actually, this is also what you will find in many of the specifications by the laser scanners. So if you go to the Leica P40, Leica HTS 6100, or the Trimble XT5, or for example, you will find these values in the specifications with certain resolutions. So how to decide on a proper scanning resolution? Well, just as a rule of thumb, I'm giving you this table. I don't remember where I found this table, so if you really want to know, it's from an article. I think it was an Austrian or a German article, but I'm not quite sure about it, to be honest. But it will give you an indication of, okay, what is the dimension of my feature? For example, if I have here a feature of 1 meter, 1000 millimeters, 1 meter, and I would like to measure it, because it's a ditch, I want to measure it using laser scanner, then I will have, as some kind of a rule of thumb, a resolution or point sampling of 35 centimeters up to 5 centimeters in this case. Or you can increase or decrease the feature size, and of course, as a function of that, you will decrease and increase the point density relatively. So here, just as some kind of an indication about that. And then after site preparation, so we know where to put our scans, we know where to put our scanners, we know where to put our targets, we know our resolution and our project parameters. Then we can finally do our object scanning using all these parameters. And most of the time, because of the fact that we have a certain resolution for the entire scan, Most of the time, you will also find an option to explicitly measure your targets with the highest resolution. So what will happen there, for example, that's the system that I used with the C10. I used the medium resolution dome scan, a full dome scan of my environment. So just putting my scanner, setting my horizontal view and my vertical view at the most optimal size with a resolution of, with a medium resolution in that case. And then afterwards, I can point my laser scanner in the direction of my first target, my second target, my third target, etc., etc. And these targets are then measured at the highest accuracy. And the interesting thing is that here, that most scanners will automatically detect the centers of the targets itself. So actually, the coordinates of your targets are automatically incorporated in the point cloud itself. And that's a very useful property that you can use for the point cloud registration. Optionally, after the scanning, you can do your target measurements. Of course, you have to make sure that these targets stay stationary for the entire duration of your measurement. So if you measure a target and somebody is accidentally taking the target, or not accidentally, you will lose that target. So you will have to exclude that target from your point cloud and data processing. Very important to keep that in mind. And then after the measurement, of course, you will have to check your coverage, the completeness of your data set. So make sure that as soon as you leave the site, that you have all the data that you want. Voila. So here's some impressions of scanners. These two scanners, or these two images, are images taken by myself. So this is an old monastery, or an abbey in Ghent, and a railway tunnel somewhere in Belgium, I think, under the international airport, and some other scanners, Scan Station 2 of British Heritage, and a scanner, I think this is a Faro scanner applied somewhere in the world. So then we have our data, we have our targets. We have to think now about, okay, how to archive the original data. Always make sure that somewhere on your computer or on an external hard drive or in an NAS server, that you have your original data somewhere, that as soon, if something happens with your deliverables, that you always can go back to your original data. And believe me, my experience has learned that it is extremely useful to have your original data archived somewhere. You don't use it every day, but as soon as you remove the data, be sure that just a few weeks afterwards, you will need those data again. So this is something that is important to stress out as well. Also, original data is very handy, but if you have no idea what the data is, or what the content of the data is, it's not very useful after all. So it's very good here to add some metadata in digital form, optionally a hard copy of your data report that you put in an archive somewhere. But digital is also very good in this case, with it just some limited notes about, okay, these data are acquired on that date by this operator with this resolution. I use this scanner. And it was within the framework of this or this project, that you can keep track of your data. Remove erroneous scans and noise. The more you remove on forehand, the easier it will be to process your data. And also select the desirable data format for exchange. It's actually the same as what we discussed during the presentation on photogrammetry. Make sure that you have a data format that is easy to use. Regarding the metadata, I always make sure that if I have my metadata, I have a general description of the object itself. So what did I scan? When did I scan it? Some spatial information about it. What were the coordinates? In what coordinate reference system was everything measured? Some administrative information, like I told you, who was the operator? Was in the framework of this and this project for this and this institute, I performed my 3D laser scanning. And also technical metadata about the scanner, about the brand of the scanner, about optionally the use of software. Actually, this is very comparable to the processing report that you will find with Metashape. But in addition to that, I would advise you also to incorporate some of the general descriptive information about the site itself, which is obviously not part of the Agisoft metadata file. On data formats, I have a lot of discussions about the necessity of saving data in an ASCII format. I think I might have a point cloud somewhere in ASCII. No, I don't think, no, I removed it, I'm sorry. But this is very important because ASCII has the advantage that you can just open your point cloud in a notepad editor or in any text processing software. It's obviously not recommended, but if you open it, you will just have a file where you have line per line the coordinates of that point accompanied with the intensity values and or with the RGB value. So it's all human readable, but that's an advantage because it's human readable. And if you are a programmer, it's very easy to program your own applications on top of that. The big disadvantage is that it can get very voluminous. So the amounts of space required to save your ASCII data, especially with large point clouds, is very large. So you need a lot of space to save your data. And also the conversion of these ASCII-based data to a format that is native to the software that you're using, like in Cloud Compare or in Cyclone or in HealWorks. That will also take a lot of time to import your data. So in most cases, it's advised to work with a binary format and preferably a binary format that is open access. So for example, here, I mentioned the LES format if you're working with airborne data, or the E75 data format that we are also using in the demonstrations. These are open formats that are open specification published on the internet, so you can use them, you can modify them. You are not stuck with one or one single scan vendor or software developer. Then a little bit on data quality. I will not go into too much detail because actually you've already seen a lot about this. So some definitions here is on resolution, which is actually the average distance between X, Y, Z coordinates in a point cloud. So the average distance between points in the point clouds. And actually the resolution here, I refer again to this table, this indicative table that I gave, and the equation that you have here. So a quality measure is actually a value, an index value that you can use here as a function of the point density on one hand and the object size on the other hand. Precision is here related to the distribution of the measurements around about the average value. So it's actually some kind of a standard deviation, a spread around the true value, or your average, sorry, not your true value, the average value of your surface. And it's also called the random error or the noise on your surface, also mentioned in the previous presentations. And then trueness or correctness is a value corresponding with the deviation of the mean value that you measure and the true value. So for example, if I measure my background here, I use a total station to say, okay, I have a surface, I make a scan of it, then the noise of my scan on the surface is the precision, and the average of my point cloud in relation to the true coordinates that I measured with my total station, that is a value of measure for the trueness or the correctness of the data. And then the combination of these two, so the combination of precision and trueness, or precision and correctness, that is actually something that we'll say about accuracy. So the accuracy, at least from the definitions that I use, are a combination of precision and trueness. It's actually give you something about the entire distribution of your errors. Instrumental errors, I already said in one of the first slides, I will just go back to this slide here, that a laser pulse or a laser signal is not an infinitely small pulse or signal. It has a certain width, and this width will vary as a function of the distance from the scanner to the object, and it will function as a function of the incidence angle. So I give you this equation just as for the sake of completeness about the relation between the wavelength of your signal and the distance and the opening angle. So you have a beam width, a distance, and then as a function of that, it will your beam divergence will vary as a function of the distance, which is of course variable in your data set. And why is this so incredibly important? Not only for the quality depending on the incidence angle, but also for this effect that you see here. It's the so-called mix effect. If you have, for example, a corner of an object, so you have this point with a total station, it's very easy. Let me take something else to illustrate it. If this is the corner of my construction, and I'm having my total station, with my total station, I can measure exactly this point of my object. So I have my coordinates of that object, but with the total station, or with the laser scanner, it will just measure, 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 measure. And even if you are lucky and the beam spot will just get here, you will actually measure this position here, or this position here, or this position here. And especially on these etched surfaces, you'll end up with a certain amount of mix effect. So what will you actually measure? Will you measure this part of your surface or this part of the surface, or will you measure somewhere in between? And that effect is heavily depending here on the beam divergence. Some other instrument errors or errors related to the sensor itself. I'm not going into too much detail about it here. The color, of course, has an impact, already mentioned also yesterday. Please remember the scan of the room that has been presented by Michele. The function of the color, the influence of the color, the influence of the material that is reflecting your laser scan signal, and the incidence angle has also been mentioned. Well, actually, that's also mentioned here. We have a signal here. So let's say that we have a signal coming in, reflecting on this surface. Of course, we want the echo of that signal, but given the fact that we have a so-called Lambertian reflection, so that's actually what you see here. There's a lot of energy also going in the other direction, a specular reflection that you will have, for example, with a perfect mirror. If you look on a mirror, you will have specular reflection. There is general diffuse reflection. And one part of the diffuse reflection, this Lambertian reflection, is actually what we will receive with our echo. And that is why if you are scanning very smooth surfaces like a mirror, you will have very bad results. If you measure very dark surfaces, you will also have very bad results caused by this property. And then next to the instrumental errors, you will also experience some additional errors related to the environment, especially in in very hot environments where there's a lot of temperature gradients between, for example, a ground surface and the air on top of it. Then you will have these air deviations. In this case, forgot the name of this, but it's actually distortion of your light signal. So the temperature, atmospheric deviations, interference, distortion by motion. So this is related to the stability of the object, but also the stability of the scanner, but also the stability of the object you're scanning, and that will become clear while working on the demos. And some errors related to site preparation, so suboptimal scanning setups, unstable stations, scanners that are not properly calibrated, oversampling, so the resolution is too high, and points are overlapping each other as a function of the distance. And then, of course, errors related to methodology, registration, and processing. So we're almost done with the data management, or at least I will almost stop with the discussion on data management. So we can talk about a little bit about data processing. So everything that we just said, so all the site preparations and the parameter setting, etc., 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 that comes on top of this. So that's actually excluded in this schema. This is actually only dealing with the data processing. So we have our survey measurements, which are topographic reference measurements of our targets, of our topographic background. We have the sites on scanned by our laser scanner, and using these two data sets, in some cases this is obviously not available, or this is not mandatory to have your survey measurements by means of topographic measurements, but you can also use just only the scans of your site and your targets. Then the scanning registration will take place. That's something that we will discuss in the next presentation after the break. And then afterwards we can do our filtering, data filtering. We'll cover that tomorrow, and we'll work on our deliverables. So clean point clouds, rendered image, animations, meshes, 2D or 3D drawings from AutoCAD. It's, for example, also possible, as also mentioned yesterday, to incorporate point clouds in software like Revit, mesh decimation, and it also comes with segmentation, so extracting relevant information out of your point cloud and classification, ground points, non-ground points, what is part of stone masonry, what is part of wooden constructions. These are all interpretative work on the point cloud itself. So registration is something that we will definitely discuss after the break. What you can find more in this presentation is just a little summary of the data registration. I will not go into too much detail because this will be discussed after the break on data registration, but just for your information, this will be covered. And then data processing. This is something that we will do tomorrow, the noise cleaning, subsampling, or resampling, and a bit image classification is for tomorrow. So here, image classification, point cloud filtering for tomorrow. Difference between 2D and 3D, and the deliverables, but we actually already covered this, but this will be for Thursday. Sorry, also for Monday, for tomorrow. So let's have a little break here. The rest of the information here is just for just to be read by yourself. I will not go into too much detail because I really want to get started with the registration. Just to end this part of the presentation, I would like to show you this schema. So this is from a book called 3D risk mapping. And it gives you some kind of a workflow on laser scanning itself. So it will show you, it's a flow model to say, okay, is my quality control correct? If not, I have to go back. Have I measured all the targets? Then I can move to the next position, blah, blah, blah. I can do my traverse calculation. Patati patata, registration is included. And then at the end, it will give you a very simple workflow on deriving your deliverables. So deliverable, client feedback, is it okay? No, you have to go back. Quite straightforward, but also very useful to use as some kind of a background system for your data acquisition and data processing. And of course, at the end, defining your deliverables and getting feedback from the project owner. Voila, I would like to stop here. It is 5 o'clock. So let's meet again in 10 minutes, unless you have any questions. Do you have any questions?
Nope.
I hope.
No.
What did you say?
I hope my presentation was clear.
Yes, yes, yes.
Wonderful.
Yes,
You,
it was.
you have a very rhythmic voice, so it's easy to sleep. See you in 10 minutes.
Yeah, 5:15 Central European Time.
Okay.
Let's continue again. In the second part of this lecture, I would like to talk about point cloud registration. Much of it has already been said about this topic, but I think it has been good to go into a little bit more detail about it. So registration, what are we talking about? This is actually the process of linking measured point clouds from different scan stations. So we have different scans scattered all over our study area, and we will use registration, point cloud registration, to merge all these scan stations into one spatially coherent system. It's actually, from that perspective, quite comparable to what you will see with georeferencing. Share my screen. Voila, screen is shared. So it's the process of making different point clouds spatially coherent, and it actually defines a set of translations, rotations, and scale parameters for each and every point in our point cloud collection. So the question here is, okay, how can we do that, and what is the most suitable registration method, and what methods are also implemented in Cloud Compare, and what can we use by ourselves using Cloud Compare in that, for this purpose. So we apply it on point clouds in the case that our point clouds are not georeferenced on forehand. Technically, is this possible to make a scan of an environment, put your scanner at a certain fixed position, and directly link your scan to targets that are also topographically measured. So in that case, you have your coordinate reference system fixed. But in most cases, and especially with terrestrial scans, that is not the case, and you will have to assign coordinates to each and every point afterwards. The more modern laser scanners have the ability to automatically register your point cloud. So you make a scan, you measure your targets, you go to the next scanning position, you measure your targets again, and the scanner automatically calculates these transformation parameters for you. So there are actually two ways of doing that. Either way, we can use the targets that we already mentioned in the previous presentations and in the previous presentations that were presented the other day, or we can use a cloud-based registration, so corresponding points from other clouds or clouds that are closest to the cloud that we want to register. And I will discuss that in a little bit more detail in the coming slides. And in that, by doing that, we have the option to actually assign absolute coordinate reference systems to our point clouds. So this is actually the same slide that I already showed you in my previous presentation. And what we do here is actually talk about this part of our process: scan registration, merging multiple scans into one coherent collection of point clouds, or the process of making or relating point clouds to a coordinate reference system. These are actually two separated things that we will cover in this presentation. There are two main ways of registering point clouds. We have at the first part of this schema, we have the direct georeferencing or direct point cloud registration. And in that case, what I already said, we set our our terrestrial laser scanner over a known control point. So we have this nail, this metal nail somewhere, of a marker on the ground somewhere. We set our laser scanner on top of that marker. We measure the distance from the scanner to the marker, and we know our position. And then during the data acquisition, we also have to make sure that we can set our orientations correctly using pre-measured ground control points or pre-measured targets. So that's just a very conventional way of registering laser scanning, but it's quite labor intensive. It's also actually very comparable to the thing that you would do with a total station or with conventional topographic measurements. More commonly, we will use the indirect point cloud registration, where we will use either target-to-target constraints. So we use the targets that we measure as a basis for our registration. You have multiple targets in one scan, multiple corresponding targets in another scan, and you will actually make a combination of these targets, and that will result in a translation, rotation, and scaling parameter, scaling matrix that we can apply on the different scans. And then optionally afterwards, if you have a series of targets that have absolute coordinates assigned to them, you can also have coordinates in a certain coordinate reference system. Another thing that is very useful as well, and that's also one of the topics that we will discuss in the demos, is a cloud-to-cloud registration, where you say, okay, I have a point cloud, I will detect certain shapes or certain distances in this point cloud, and I will relate them to the corresponding part of a consecutive point cloud. So you'll actually use the properties of one cloud, find the match between the properties of another cloud, and then it will iteratively find the best possible solution for the registration. In that case, it's very important. We are not using targets here, so we are not using these black and white targets or spherical targets. But in this case, we need enough overlap between consecutive scans, approximately 30% at minimum. More frequently, I increase that value a little bit to 40 or 50%. And we will see in the demo that we will even use 50 to 70%. And then afterwards, also here, it is possible to absolutely georeference our point clouds using net roll markers in this case. So the direct registration of point clouds, if you have your tripod, you make sure that the tripod is leveled on top of a marker. These are these copper nails or metal nails that you will find on the street a couple of times, or if you have a marker placed on the surface, make it sustainable, that you're just self-referencing your scanner on top of that object. But it's quite labor intensive. So if we talk about this indirect point cloud registrations, and especially when we talk about the cloud-to-cloud registrations, there are actually also here two transformations that we can apply. And most of the time, we will use the Reged transformation. A non-Reged transformation is a transformation where we have a non-linear transformation, and this transformation will actually modify the shape of our point cloud. So definitely when you're working with a laser scanner where a priori the geometry is measured correctly, so you do your measurements and the distances and all the Cartesian coordinates that you derive from these measurements are a priori correct. In that case, it is absolutely not recommended to use a non-Reged transformation, because you will entirely stretch your point cloud, which will modify the actual shape of the object that you're measuring. When is this useful? You can use this actually when the true geometry of the shape is not correct on forehand. So if you have, let's say, for example, a very bad image, or an image with all the distortion still included in that image itself, you will actually use a non-Reged transformation to correct for all the lens deformations and scanning deformations that are included in that part. So actually, if you put it very strictly, this is something that you will frequently find when doing a georeferencing in GIS, for example. For point clouds, so for 3D point clouds, especially acquired by laser scanning, but to some extent also acquired by photogrammetry, we will use a Reged transformation, a linear transformation, where the distance between points or distance of points within the point cloud will not change. And even if we change them, like in photogrammetry, we will use vormigheidstransformatie, a deformation in equal direction. So if we scale the x, if we apply a scale on the x-axis, we also apply the same scale parameter on the y and on the z-axis. But most of the time, of course, the scale parameter is something we will not touch. We will only translate and rotate our point clouds because our measurements, especially in laser scanning, are a priori correct. So actually the main concept here is that we have two point clouds in 3D. So we have x, y, z coordinate in all our dimensions in x, y, and z. We assume that we have one point cloud that is correctly georeferenced, and we have a point cloud that needs to be registered. So we have a master and we have a slave, and we will modify the slave as such that actually the minimum distance of the distance from all the points in one cloud to the corresponding closest points in the other cloud, that these distances are actually minimized. And there are some tools, some mathematics behind that. You can use least-square adjustment transformations to actually translate and rotate your slave as such that the distances are minimized in relation to your master point cloud. So least squares are very important for this approach. And for this rigid transformation, for this least square adjustment, actually, there are two approaches. So we can use the correspondence-based registration, and this is where we will use ground control points and or targets, or we can use simultaneously pose and correspondence registration, which is actually a cloud-to-cloud registration where we will just iteratively fit one cloud in another and continue that process until a certain optimum is reached. And actually, these two steps these two steps are something that I will demonstrate in the coming two demos. So the correspondence-based registration, that's the most easiest one. What is actually happening here, you have a set of coordinates. These coordinates are coordinates from your target, for example. In real coordinates, you have the scanned coordinates, so the local coordinates, and you will actually try to find translation. So this is your translation here. You have a rotation and you have a scaling. And you will try to calculate the values of this transformation, and then the local coordinates can be converted to absolute coordinates. Well, luckily for us, there are two very interesting things. Well, first of all, since we are working with a laser scanner and since the distances are a priori correct, we will set this scale parameter to 1. So we will just eliminate this, this last parameter. And also, because of the fact that we level our instrument, we also have an additional constraint, namely that for all the scans, we will have our z-axis pointing upwards, so we can only rotate in our horizontal plane. And this is another very interesting constraints that we can use for our registration. And we have to memorize it because these parameters will come back while working in Cloud Compare. So a scale factor of 1, and the rotation will only take place in our along our z direction. So the equation can heavily be simplified, as you can see here. Then correspondence-based, what you actually do here is work with a single station and then use local coordinates and georeference coordinates. So this is actually the first situation that we already discussed, where we have our total station positioned on top of a nail or a georeferenced a geodetic point. Or you can work with a chain where you also always measure the next point where your station will be positioned. But these two are not very convenient in practical terrestrial laser scanning. Most of the time, you will work with some kind of a resection where you have your scanner at a certain position and you have your targets positioned around your scanning position. So there's actually a resection that will take place from that scanner with orientation 0, 0, 0. You will assign your coordinates of the targets in local coordinates. You will measure them from another station, the same targets, and you will have these coordinate pairs that will allow you to calculate these translations and scale parameters, translation and rotation parameters. So that's actually what's happening here. Target based, you have a scanner. From that scanner, where the origin is situated in the center of the scanner, you measure your targets. From another scanning position, you measure the same targets. You have two target pairs, and you can calculate the transformation between them. A very interesting way of working with laser scanning without using these targets is the cloud-to-cloud registration, which is a priori, I would say, less accurate, but also, so it's less accurate than target-based, because we will not explicitly measure our targets or our reference with highest accuracy or highest resolution, but we will use the entire data sets for the registration, for the self-registration actually. And of course, since we are using the entire registration, the quality of our process is hampered also by the resolution of our point cloud itself. So what's actually happening here, we have our point cloud, let's say a master and let's say a slave. So this point cloud is already referenced correctly, or we consider that as our base point cloud. We have our slave, so the point cloud that we want to register as a function of our master. And what's happening then is that we're actually looking for correspondence. What points in PS are closest to the points in PM? And then based on that, we can actually apply a transformation, the first transformation of PS, and then we will look for new correspondence between S and P. So PS modified against the master. We do the process again, look for the transformation, and then we say, okay, is the distance between my slave and my master lower than a certain threshold? If that is the case, then we are ready. Then we have our transformation. If we are not ready, we use the transformation as a second initial transformation, and we just loop through this process until the points are closest to the master point. So here, just in pseudocode, what's happening. So we have our slave, we have our master. We will look for correspondence. So we have closest points between the master and the slave. And all these distances between the master and the slave, all these corresponding points should be minimized as long as a certain threshold is not reached. So here, another illustration of that. If you have a master point cloud, for example, here, the green point cloud, let's say that that's a raw point cloud, and we have an orange, a blue, and a red point clouds that have to be merged on top of that. It will iteratively look for correspondence between each and every object until a certain optimum is reached. But of course, using this technique, we need a certain amount of overlap between the master and the different slaves of our point cloud. So in order to use these both techniques in Cloud Compare, there are different tools available to do that. So first of all, we can use a point-based alignment. So we can use ground control points, assign them in our point cloud, and give the absolute coordinates to these points. So that's something that I will show you how that works. We can also manually translate and rotate our point cloud, which is very good as some kind of a pre-alignment. Let's call it a pre-alignment to start further processing, further alignment, further registration. And we have, of course, the level point clouds that you have experienced in the previous exercise when you were working on the the scriptorium of that point cloud. And the point cloud was tilted. You define 3 points in your point cloud, and it will use these 3 point clouds, these 3 points as a leveling plane for the rotation of your cloud. Of course, never apply this technique when you are working with a terrestrial laser scanner where the Z-axis is correctly aligned, because if you have a terrestrial laser scanner with the Z-axis correctly aligned and you apply this level point cloud, you will actually rotate your point cloud around this in the horizontal plane. So your entire point cloud will be tilted, and this is definitely not something that you want in for the registration of terrestrial laser scanning data set. So if you have translated and rotated your point cloud manually, you will have to fine-tune this the registration, optimize your registration between the slave and the master, let's say. And in that case, you can use automatic alignment or iterative closest points algorithm or cloud-to-cloud registration in Cloud Compare. And that's what I will discuss right here. So do you have any questions so far, or would you like to see what I will do in Cloud Compare? Then in the steps that will come, I will first very briefly go through the slides. I think that's a good idea. So in the first presentation or first demonstration, I have an unreferenced point cloud of an archaeological excavation. Let's assume that this point cloud has been taken by a laser scanner. In reality, this is not true because this is covered, these data are acquired using Agisoft, so it's an image-based point cloud. But let's use it as a laser cam point cloud because we're talking about point clouds in this case. And in this point cloud, you will find different targets, different black and white targets, and we will use the corresponding coordinates of these targets to actually georeference the entire set in the Romanian coordinate reference system. So that's what will be discussed here, and I will just guide you through the process. So that's what I will do here, and then I come back to my presentation. So here's my point cloud. I just downloaded from the demo folder. I take a top view, and if you zoom in on this point cloud, you will see. Let me zoom in a little bit, or increase the point size a little bit. You see here these black and white points. Of course, if I start indicating these points, the quality of my indications will be limited by the point cloud density. So that's definitely something that I have to take into account in this case. There are software packages that will allow you to automatically detect the center of your targets, so the center of the black and white targets, but Cloud Compare, until the best of my knowledge, does not have that function yet. So we will detect these points or indicate these points. That's one task that we will have to do. And if I go to the data here, you will also find a PNG file with an indication of the location of the points. And here you have a point cloud or a point file with the XYZ coordinates of each and every point. So this is actually the situation that will allow me to start. So I have my point cloud, and here I have several options available to start my, my alignment. So we already saw this increase it again. We already saw this function, so the translate and rotate. So we will not cover that that here. We will just use here align 2 points by picking at least 4 equivalent point pairs. So that's what we will do. This is actually the target-based registration that we will be working on. I will first select my first points. So right now, you see that I'm here at point 8. This is point 7, point 6. So then this should be point 1. I will zoom to point 1, and I will open my alignment tool. And this alignment tool, let me increase my size again. What you see here, you see the 2 align entities. So this is my slave. These are my slave coordinates. And this will be my master coordinates, my reference coordinates, my true world coordinates. So what I can do here is I can select a certain point. Let's take it at the center of this point. So now I have here A1, it automatically says A1, and A1 has a local coordinate of 51.53, 5.26, and 5.22. So this is my first point. I correctly labeled my point, so I can just go to point 2. This is point 2 in this case. Go here, and I will select point 2. Then I go to point 3. So let me take here point 3. Point 4 is here. Let's take point 4. Point 5. You see that I'm really zooming in order to get the best possible candidate for my point, which is still not very convenient because of the low resolution of my point cloud. Point 6. 0.7. And last but not least, 0.8. Let's say that this is 0.8. So that's the first step. The next step that I have to do is add a reference point. And my first reference point is obviously ref 01. So that will be the first point that I indicated here. So let me take the X, the Y, and the Z. So far, by the way, I have not seen I have not seen an option to directly load your coordinates here in this screen. So I have to do it. I have to do it manually. I take a second point. And you see that R1, R0, R1 are now included. Let me go to R3. Normally, if I would do this in a video, I would skip this part and say, okay, now we are done. But these are live demos. And the problem with live demos is that it can be very tricky to make errors. So I hope it works. This is 4. Let's take a 5. And I only have 8 points. I don't have 100 points. Then let's take 6. 6 is R5. Seven. What is very important here is that you respect the order. So this order is very important because what we will do is link A1 with R1, A2 with R2, etc., etc., etc. Almost done. Voila, now we are set. So we have 8 points here starting from R0 to R1, and we have 8 corresponding points from A1, etc., etc. And you also see that our points are already more or less positioned here in our 3D space. So what we should do now is we should make sure that we have our rotation set correctly. So assume that we are working here with laser scan data. You should say, okay, we will only rotate around the z-axis. So we will rotate in our horizontal plane. If I say, okay, I do it in all directions, I can just rotate my position, my point cloud in all directions. And that's definitely something we don't want to do here. So I say, okay, we set our rotation to only in the z direction. And other parameters that you can set here is to translate your point cloud in X, in Y, and in Z. And in this case, we definitely want to perform the translation in all directions. So we can go in this direction, and in our top direction. As soon as I set my parameters, you also see that it will calculate some error values. So an RMS in the same units as your coordinates here. So these are metrical values. I will not set my scale, so my scale parameter will be equal to 1, and auto update zoom. As soon as I press OK, it will automatically zoom. And now I hope that if I press align, yeah, voila, I press align, and now the point cloud is, it gives me a preview of the result of the alignment. So the point cloud is now referenced as a function of my reference points. And if I agree on that, and if I agree with all these values, which are obviously related to the resolution, to the point density of my point cloud, but if I'm happy with that, I can press OK. And here I will get some information about the transformation itself. So I said, okay, I don't use a scale parameter. I've not used rotation in X and Y, only in Z. And I have a 3D translation, so a translation in X, Y, and Z. And the result of this entire procedure is an RMS, a root mean square error of 1.5 centimeters. Well, 1.5 centimeter is also the average point density. So I'm happy with that. And voila, now my point cloud is corrected. If I take now my point picking tool and I click a random point, it will tell me, it will give me the correct Romanian coordinate reference system coordinate of that point. And then afterwards, I can just save it. I can say, okay, select my point cloud, save it, and then I can say Sultana underscore ref or underscore CRS to indicate that this point cloud has been georeferenced as a function of my reference points. Voila, that's the first way of georeferencing or referencing and registering your point cloud in Cloud Compare. Do you have any questions related to that? The last things that you see here, and this is especially useful, let me close this one, especially useful when you don't want to type in your coordinates yourself. If you have a point file as the file that I have at the moment, so this one, what you can actually do is just drag and drop your point clouds. You can also drag and drop your reference points, taking into account the correct fields. So I have a label, an X, a Y, and a Z. So I apply. It will ask me for this global transformation, which is reversed after my, my work. So I say yes. And then here are my reference points, and my markers are obviously underneath it. And what I can do then is I just select my I select this point cloud. I'm not sure if I can. Yeah, I select the cloud that I want to register. So that's this point cloud. I go back to this tool. And then here you can say, okay, I want to align this one. No, just a moment. Just a moment. I think I have to select them all. Hallo? Tja. No, something is not going as it should go. Now I have to go back to this. Anyway, that's target-based or coordinate-based, reference-based registration in Cloud Compare. Another very interesting thing, and that's the last demo that I would like to share with you for today, is this cloud-to-cloud registration. And let's say that we have, in this case, also a master point cloud and a slave point cloud. We will make sure that that we roughly align these point clouds, and then we will apply iterative closest points, so cloud-to-cloud registration to register the 2 points together. So that's actually what's presented here. And the result of that is a nicely referenced point cloud. So let me just show you how that works. I will close this one. And let me go to the first point. I already inserted the first point, and it's also available on the data server. So this is scan 2. If I go to scan 2, I see normally if you load it, you will see something like this. This is the colored point cloud. So this is C10 data of NAVPRIO from 2017, acquired within the framework of this workshop and of the workshop, the summer school. And if I take the second point clouds, what you will see here is that since both point clouds are not referenced, they will all, already translated this one. So let me take point cloud 1 and point cloud 2. I was a little bit too fast. I already prepared this presentation. If I look at the points, you will see that the origin of both points are in the same, at the same position. So my 0, 0, 0 coordinate is situated right here, which is obviously not good. If I visualize both point clouds again, you will see that I have a building here, I have a building here, and there's a lot of intersecting of walls. And that's obviously because of the fact that the rotation in the horizontal plane is totally random, and that the positioning is of both scanners, the orientation of the origin of both scans is situated here at my the origin of my XY axis. So what I first do is I increase the visibility of my points clouds by setting my RGB values, so my color values. And what I can do then is, let's say that my scan 1 is my master. So I can actually rename my my point cloud here by pressing F2 or by double click or by right click and rename. And I say that S2 is my slave. And we first manually align, roughly align the slave point cloud. So I can rotate it a little bit. I can translate it. So here you see that actually my origin of scan 1 should be somewhere around here. I can just rotate it a little bit more. Be careful, by the way. Ooh, I didn't say that explicitly. By default, your rotation will be on X, Y, Z. And also here in this case, we're working with terrestrial laser scan data. So I only want to rotate around the Z axis. So if I take a side view, that if I'm rotating like this, I will not be able to tilt my point cloud in the horizontal plane. And that's very important when you start working with this. So let's continue. I have here 2 parallel lines, so I'll make them as parallel as possible, and I will fit them like this. So let's assume that this is okay. No, I did something wrong, of course. So top view, I have to reset it again. Let me pause it. Take a side view, zoom in a little bit, just to see if my alignment is okay. Maybe I will bring it a little bit up. Top view. And this looks, at least for a rough extent, it looks okay. So this is a rough alignment of my master. So this is again my master against my slave. And also if I go to scan 1 has a position assigned to it. If I right click here and I say bubble view, then this is my scan 1, or the data that I have in scan 1. By the way, these are moving objects that are not scanned in geometry, but they are photographed. So people were walking during the photograph, so they are actually just projected on the ground floor. And all these gray artifacts is noise that has been eliminated from the point clouds. So this is more or less noise free. If I add, or if I remove my second point, you see here that there were umbrellas on this side of the building and there were umbrellas here. But because of scan 2, the scan 2 that is positioned somewhere here near this building, I have a better coverage of this building as well. The same, I think the same also holds here. If I disable point 2, I have this entire series of umbrellas that I had to remove from my point cloud. And by using scan 2, I have a better coverage of my square in this case. But the problem is that I have, let me go out of my bubble view, is that if I zoom in on my point cloud, for example here, and I take this wall, just as an example, let me increase the point size a little bit, that there's still a misalignment, you see it here, a small misalignment between scan 1 and scan 2. So you see, and I can modify that manually, but that's not very ideal to do it manually. I prefer to do it for the entire point cloud at once. So what you can do then is say, okay, I have here my master point cloud, I have here my slave point cloud, so I select them both, and then you go to finally register already roughly aligned entities. So this is the button that you will find here is actually the cloud-to-cloud point cloud, cloud-to-cloud registration, and it will iteratively find the best solution for this point cloud. So very important here is that you have to define the roles in your point of in the analysis. What is the cloud to be referenced? So that's obviously my slave cloud here, my scan 2. And what will be my reference? What is my master in this case? If these are not correct like this, you can swap them. So you can say, okay, my reference is the slave and my aligned is my master. But obviously in this case, we want scan 2 referenced as a function of scan 1. Then the next parameters that you can find here is the number of iterations. How many attempts will Cloud Compare do until it stops its analysis? Or you can say, no, I will define a root mean square error. And even to date, I have no idea how to modify that value for one reason or another. So I can delete the numbers, but I cannot modify it. Very important here is the level of overlap. By default, it will be set on 100. So you will have a 100% overlap. So this is the default. But obviously, in our case, we don't have 100% overlap. Let's say that we have 50% overlap, or 50% of the objects that are covered in scan 1 are also scanned by scan 2 and vice versa. So we have 50% overlap. Adjust scale is again not recommended if you are working with terrestrial laser scanning. Only use that if you want to apply a non-rigid transformation, or a transformation, no, not a non-rigid transformation where you will scale your objects around the X, Y, and Z axis. But in this case, we leave it empty. And then here under research, a sampling limit. So how many points will be used for the analysis? By default, I think it's on 50,000. If you have a more powerful computer, you can increase that value. The rotation, once again, we only want to rotate around our Z-axis. So rotate in the horizontal plane, not in 3D, no 3D rotations. So we set it here. By default, it's set on X, Y, Z, but I will set it on X, Y. Translation, the translation on the X-axis, Y-axis, X-axis, Y-axis, and Z-axis. And this is also a very interesting one, enable farthest points removal. If you have points that are very far away from your master, so they don't have a correspondence, they definitely don't have a correspondence with your master, You can say, okay, please keep them out. So that's just a statistical analysis that is applied, because otherwise you will force Cloud Compare to look a matching point for that one. So for example, this point here is definitely not measured by scan 1. It is scanned by scan 2, but not by scan 1. So by setting this value, we can actually exclude that from our analysis. So voila, we are set. And then we can press OK. And the hardcore begins. It will actually now calculate the transformation parameters that are mentioned here. So this is actually what it is calculating now, and here is the result of that. So we have a translation matrix with an RMS of 50 meters. Of 50 centimeters, I'm sorry. So I'm not very happy with that. Apparently my values were not strict enough. And if I zoom here on this construction and I enable my scan 2, you clearly see indeed that there is still an offset between my my 2 point clouds. So even then you can just start the process again with the same options. Aligned reference, still okay, and we press OK. So we're just continuing the process with a number of points, but I'm still not very happy with it. As you can also see here. If that value keeps that high, what you can do, but be very careful with that, is just say, okay, we will not use the RMS difference, but we'll just increase either the number of points. So we will just increase the sample limit. But once again, be very careful with that, because it will take a lot of resources from your computer. And also here you can say, okay, we're not using, let's say, for example, 250 iterations on 500,000 points. And now it's just repeating the process 250 times. Still have this error. And I don't know why. It looks okay. No, it's not yet okay. No. So we just have to force our parameters a little bit more. Let's bring this to 40% and let's increase this to 500%. And let's set this to 500,000. And now it's doing this analysis 500 times. So I'm just iterating the process over and over again in order to get the most optimal results. So that's why the best option, if you have the ability to do target registration, especially a function where you have target registration, the option to explicitly detect your targets. So that is where the software will automatically detect the optimized coordinates of your of the center of your targets. That will give you the best results for point cloud registration. Now it's 10 centimeters, so we went from 40 centimeters to 10 centimeters. which is obviously much better already. And I can just continue this process until I have an optimized mesh. Eventually, if you are finished with this registration, so you will also do this registration in the exercise, please start with 2 scans and then iteratively you can increase, add another scan. So try to work in a sequential order in that case. So once again here, step by step, the different parameters, the parameters for the transformation itself, acceptable, not acceptable. At the end, when you're ready, what is very good to test your results is that you say, okay, let's select both point clouds again, and then try to make a section of your point cloud. So if I take the 2 point clouds and I make a section of my result, then under normal circumstances, you should obviously see the wall measured by 1 scan and the wall measured by another scan, that they coincide. If that is definitely not the case, then you should redo your process. So this is actually quite a good way to check, to at least visually check your results. But also you have, of course, the RMS of the transformation. That is a good parameter to indicate the quality of your registration. So normally the profiles like here, they should coincide. You can do that by selecting your sections. And then at the end, again in bubble view, if you look at the point cloud, you see one coherently correct visualization of the points. At the end, you will have 2 options, or I would advise you to work in one of the following options. So I did a lot of effort now on registering my point cloud. So what I can either do is just take my slave, which is now referenced, so it's actually now part of my master, and I can save my point clouds as a new point clouds. So in that case, it's obviously a good idea to explicitly state in the naming of my file that this is georeferenced, or I save it and mention it in my metadata. Otherwise, another option what you can do is just select the 2 point clouds and merge them into 1 cloud. If I do that, let's keep my original point cloud, or the name of my Where is it? Ah, of course. Voila, here's my point cloud in RGB. And if I take my scalar field now, then the different coloring, so the red corresponds with the points measured by scan 1, and the blue points correspond with all the points measured in scan 2. And if my georeferencing has been done correctly, this point cloud is spatially coherent, and I can just take my points, let me get out of here, take my select my merged point, save it, and then save it as one massive point cloud, including the original RGB values of both scans, as well as the scalar field that refers to the original scanning position. So it's also quite a convenient way of exporting your point clouds and make sure that you have everything in one massive point cloud. But of course, the number of points in this point cloud now is already 29 million, 29.5 million. So the number of points can significantly increase. So voila, that's it's about registration. Just to give you a sneak preview. In the exercise, or referring to the exercises, let me go there. Voila. You will see 2 tasks. So the first task is about the cloud-to-cloud registration of the different scans of Nafplio. So on the server, in the task1 folder or the task1 zip file of session 5, you will find 4 scans covering the syntagma square in Nafplio. And the idea here is to use a cloud-to-cloud registration to make all these clouds into one coherent point cloud, one massive point cloud. And I would ask you to make some screenshots and the RMS of the different steps, of the different procedures, and see how, just look at the values, look at the results, like I did it. Do the walls coincide? Is the RMS value acceptable or not? When is it acceptable? Well, it's of course related to the point cloud density. So you can work on that or experiment with that. If you really have difficulties with performance, because I truly realize that if you incorporate 4 point clouds in Cloud Compare, it can require a lot of resources from your computer. In that case, I'm also fine if you just upload some screenshots of the registration of point 1 and point 2. So if you replicate the demonstration that I just gave, try to experiment a little bit with the parameters, because I'm not explaining a recipe. I try to explain to you some new skills on the use of software. So what happens if you change a parameter? How can I improve my own results? And please try to make some screenshots and put them in a document for this task. And also what I would like to ask you is that if you have generated, and this is also an interesting thing for you, if you have generated a point cloud using image-based 3D modeling, I would like to ask you to send me the point cloud, so export the object as an LAS file and send it to me via WeTransfer. And then I will reply with a series of ground control points that I will just make up myself based on your object. If it's not very clear what the object is, also include that in an email. And then you can use the points that I will send you. Once again, just arbitrary points, and you can use them as a basis for georeferencing your object, just as an exercise. The coordinates are not very meaningful, but we don't have a laser scanner, so I think this is a very good way to find some to make it interesting. So I cannot guarantee this is a very experimental exercise. Also, if you have not participated in the previous summer school or the previous course on image-based 3D modeling, please send me an email about this, and I will send you a point cloud and additional point clouds. No, actually, you can just work. You can try to work on the point cloud of the archaeological excavation that I demonstrated. So in that case, you can duplicate this exercise. So make this as an exercise, the demo as an exercise, and in that case also try to georeference this point cloud based on the ground control points that were measured with a total station in this case. Voila, the data are available, the exercises are open. Do you have any further questions?
I'm okay.
To be honest, this is a very interesting topic on laser scanning, but also a very important one. So either if you have used a terrestrial laser scanner, but also for the registration of point clouds derived from photogrammetry, I think this technique of cloud-to-cloud registration and cloud-to-target registration is something very very important to master, also for data inspection. Well, then I will stop sharing my screen again, and I will stop the recording.